I'm going to take a break here from the middle of this game to describe a program called spiderwing that I wrote, a C program um, that is occasionally handy. I don't consider it cheating. I don't actually use it hardly ever, but it started out as basically a whining program to say, "Oh, come on! I can't believe that all I got were queens, and where are all the tens?" In other words, some measure of what kind of bad luck did you have. So the mechanics of it are here. If you look up here, you can see in my command line window, I typed spiderwing in the directory that I'm in, and I then type a series, basically type in all the visible cards. And I can, for instance, I start with 8, ace, a hyphen 9. So here's the 8, the ace, and 8 and 9. This indicates that it has that whole sequence. And then I can type in the other cards, 4, 3, 9, ace, 7. And it's tedious to some extent, but you get a little benefit when you actually do have a long sequence. Um, so that's how you do it. And then what I did, what I intuitively thought of as bad luck is when you have adjacent ranks where the counts are quite different. Imagine you have 13 cards, ace, 2, 3, ace to king. Well, that's all very nice, because everything matches up. You've got one ace to go on a 2, one 2 to go on a 3. But if you, for instance, had two aces, two threes, two fives, two sevens, two nines, you'd say, oh, that's terrible. That's terrible, because they don't match up. And there may be better ways to measure it, but one way I measured it is I basically look at the number of steps between adjacent ranks. So after having put in all those cards, there's a little table here below that says remaining of the following cards, and it gives the counts of the remaining cards. Here it's 3 aces, 3 twos, 2 threes, 4, so forth. And now what I would call the bumpiness here is the difference between adjoining ranks added up. So 3 minus 3 is 0, 3 minus 2 is 1, 2 minus 4 is 2, using absolute values here. So we have 1 plus 2 is 3, plus 1 is 4, plus 1 is 5, plus a whole bunch there, plus 3 is 8, plus 3 is 11, plus 2 is 13, okay? So the bumpiness here is 13. And then basically what I'll do is take this number of cards and, deal them out 10,000 times, deal that number of cards and compute the bumpiness and find out, well, how much of the time is it worse than this, or is it better than this? How much of the time is it better than this? And in this case, we get a 0.11 or 11%, meaning this is actually a more even distribution than you would expect by chance alone. And where the original, oh come on, what's the story, comes from, then if you see a value here like 99 or 98 or something, then you'd realize that according to this metric anyway, boy, you got really uneven distribution. So that's what it originally was for. But one thing that it can show you here is also just more mundanely, what ranks are you short on and what do you have lots of? And you can obviously just do this yourself, but this does a little of the bookkeeping for you. And for instance here, if you look, you notice this remarkable bump here in the fact that there are 5 tens still in the deck, and only 2 nines and 2 jacks. So in a sense, we're glaringly missing 3 tens. Okay, and I mostly I just bring it up when I want to whine and say, gee, did I get bad luck? I certainly couldn't in this case say that I got that kind of bad luck anyway. But that's what for some reason I called the spiderwing program, and it's one of the tools I have to check these things. If, for instance, you have suits you've already removed, then in the count you just enter them as A to king, because they're cards and you've seen them, so that's how they count. And so with that, I've introduced the spiderwing program, which I could make available to anybody who really wanted it. It's just a C program made from a compiler, vintage 1998 or something, but it works. Uh, so there, that's spiderwing.